Good morning, everybody. Today we are going to learn about propositions. This is from chapter 1.1. It falls into section of logic. Also, this video lecture is presented by Star Academica. And if you have any questions, please send an email to this address. We'll be very happy to answer you. Okay, so what is a logic? Logic is the basis of all mathematical reasoning and of all automated reasoning. So it's an important subject. Practical applications of logics are designing of computing machines, specification of systems, artificial intelligence. Logic is used in computer programming and in all programming languages. To understand mathematics, we must understand what makes up a correct mathematical argument that is called proof in mathematics. So if you are going to claim something, we have to have a proof. We need to prove it and make sure that everybody understands that proof. Once we prove a mathematical statement, it's true, we call this a theorem. So if a statement in mathematics is true, that's called theorem. The rules of logic give precise meaning to mathematical statements. These rules are used to distinguish between valid and invalid mathematical arguments. So let us define proposition. A proposition is a declarative sentence. What do we mean? It's a sentence that declares a fact that is either true or false, but not both. So when the sentence declares something, we have to be able to conclude that it is true or it is false, but not both. And if this is happening, then we have a proposition. For example, Washington, D.C. is the capital of the United States of America. Is this true? Yes, indeed, it's true. So this is a proposition. Toronto is the capital of Canada. Is this true? Yes, it is true. Then this is a proposition. 1 plus 1 is equal to 2. Is this true or false? It is true. Then it is a proposition. 2 plus 2 is equal to 3. Is this true or false? It is false. However, it is a proposition. A proposition can be either false or true, but not both. Okay. The followings are not propositions, and let's see why. So, if you write down a sentence, it doesn't mean that you are going to write down a proposition. What time is it? Okay, so is it true? Is it false? We cannot say. So just a question sentence. So this is not a proposition. Read carefully. Also is not a proposition. X plus 1 is equal to 2. This is not a proposition. Why? Because it depends on x. If x is 1, it is true. If x is 3, it's not true. It's false. So as it is, we cannot say whether this is true or false. So it's not a proposition. X plus y equals to z. Also, it depends on x, y, z. And what are they really? So we cannot judge whether this is true or false. So this is not a proposition. A key to distinguish between being a proposition or not, ask whether it's a true or a false statement. If you cannot answer or there is no meaningful way to answer that, then it's not a proposition. Here we don't have an answer. Here we don't have a meaningful answer really. So these are not propositions. We use letters such as P, Q, R, and S, small letters, for propositions. Okay. We'll see in a moment. We'll have plenty examples. And try to understand the negation. Negation symbol looks like this. Okay, if we are given a proposition P, so this is a statement which is true or false. The negation of P denoted by, okay, not P really, however, this is not going to be the one that we are going to use, will be this one. So this is how we are going to denote. So this is not P, it's read as not P, or sometimes the books, or even we may use this bar notation, or P prime notation. So we have three ways to represent not P. Negation of P. What does it mean in English? It means that it's not the case that P. It's not the case that P. And there are a few more ways to explain negation P, not P. The proposition not P is read as not P. I have been already reading this way. So if P is true, then not P is false, and vice versa. So if not P is true, then P is false. Fine, or here, let's have an example. Find the negation of the proposition 1. The smartphone has at least 32 GB of memory, and express this in simple English. So let's try to negate this sentence, this proposition. Okay, one way to do is it's not the case that, remember P, so this is P, the proposition P, we can give a name to this, call it P. So it's not the case that P, so it's not the case that the smartphone has at least 32 GB of memory. Okay, it's not quite common when we use simple English in daily life. We can express this in different ways, such as the following. The smartphone does not have at least 32 GB of memory, or even simply the smartphone has less than 32 GB of memory. Maybe this is the most common way of expressing in English, but we are not really going to be interested. But these are all three equivalent ways giving the same meaning. Okay, we are going to use tables to simply represent the propositions, values, true or false values, and also manipulate them. So this is going to be our first example. A proposition P can be true or false. We don't have any other option. If P is true, then the negation will be false. So this is the negation of P. If P is false, then the negation will be true. Okay. And also, instead of true, sometimes we use 1, and instead of false, we use 0. This is also very common, but in these lectures, we'll stick with true and false notations mostly. So if P is 1, not P is 0, true, false, false, 0, true, 1. Okay. Now we are going to learn some operations between the propositions, and the very first one will be the AND notation. The AND notation is upside down V, like this, so we are going to call it AND. And we are going to use this to combine propositions. Given two propositions P and Q, the conjunction of P and Q, which is denoted by P and Q, is the proposition P and Q, really. And what is the truth value of this new proposition, which is a combination of P and Q? This new proposition P and Q is true when both P and Q are true and false otherwise. So if P and Q is true, then the result is true, otherwise it is false. Again, in a moment we are going to see a table, but let's look at an example. Given two propositions, P is Alice lives in DC, Q is Alice is 17 years old. Okay, and if we want to use conjunction for these two propositions, the sentence, the new proposition will be Alice lives in DC and she is 17 years old. Okay, so if we negate one of this, so here is P and here is Q. If we negate one of this, then the result will be incorrect. So when we combine with the AND, both must be true to get the true, valid statement. Otherwise, it will be incorrect. For example, if we say that Alice lives in DC and she is not 17 years old, then this statement is incorrect. It's false. Here is a truth table for disjunction, for conjunction, really. Okay. So we use conjunction. Okay, and this is Q, by the way. Yes, it's Q. So if P is false and the Q is false, then P and Q is false. The only way when P and Q is true, if P is true and Q is true, then the result is true. Otherwise, it is always false. So we have 4 combinations for P and Q. We have 4 combinations: false, false, true, false, false, true, and true, true. So if you have 2 propositions, we are combining, we have 4 cases. Okay. Disjunction is the V notation, and we read this as OR. So we can now have P and Q, 2 propositions. The disjunction of P and Q, denoted by P or Q, that's how we read it, is false. This is false when both P and Q are false. If P and Q both are false, it is false. Otherwise, it is true. Let's look at an example back. Given 2 propositions, P. Alice lives in DC, Q. Alice is 17 years old, then the disjunction of these 2 propositions, P or Q, is basically Alice lives in DC, or Alice is 17 years old. And in order to write down something which is incorrect or false, we have to negate both. Okay, I mean, we have to have both to be incorrect. Otherwise, it will be always correct. For example, Alice doesn't live in DC and she is not 17 years old is incorrect. Otherwise, if you say Alice doesn't live in DC or Alice is 17 years old, then still, since one is true, the whole thing will be true. Okay, so how does the truth table looks like? Again, we have P and Q, and we have 4 cases: true, true, false, true, false, false, true, and true, true. Only when both are false, we have a false result when we take P or Q. Otherwise, it's always true. Okay. Another operation between 2 propositions is the exclusive OR notation, which is often used in engineering. We call it XOR notation simply, and as you see, we have a symbol for that. It's O plus. Okay, so what does it mean? As a result, given P XOR Q, then this is true when exactly one of P and Q is true, not and is false otherwise. So whether if P true and Q is false, true, false, or if P is false and Q is true, we have true. Otherwise, it is false. That's what it means. So let's look at English example. This book is interesting, and the proposition Q says that I'm staying at home. What does P exclusive Q really concludes? Either this book is interesting or I am staying at home, but not both. That's what it is. Okay, so we need to give some time to understand this. And the truth table comes like this. So if one of them is true, we get true. Okay, P true, Q false, or P false, Q true. The result is true. But if they are both the same, whether they are both false or they are both true, we have a false statement. Another important operation on propositions, it's implies to or implies. However, this is going to be read as P implies Q. Mostly I may use this way of expressing, but it is also commonly used as if P then Q. So if P then Q is the common way of using this new operation that we are just learning on propositions. So what is the truth table of truth value of this new combination of 2 propositions? So if P then Q is false when P is true and Q is false, otherwise it is true. So if we have P true, if P is true and Q is false, if true implies false, then this statement is false, otherwise it is true. Okay, and this is a conditional statement because we have an if, it depends on something. So the first part, the first proposition is called hypothesis or antecedent or premise. Okay, so this is given and the result is Q, which is called the conclusion or consequence. Now this is very, very important in mathematics. We'll be using this in the future a lot. Okay. To understand the conditional statements, this may be a little bit more complicated than the other ones. Let's look at an example. If I'm elected, then I will lower the taxes. Suppose somebody who is going through the election promises the following: if I am elected, then I will lower taxes. So this proposition, as it is, if he is not elected, then he may or may not lower the taxes. So as a complete statement, then that will be true. I mean, if he is not elected, then he lowers the taxes. It doesn't have to. There is no condition. The only thing which he makes a promise, if he is elected and he is not lowering the taxes, then the statement will be false. Otherwise, will be true. That's the interesting part about this. Another example is if you get 100 on the final, say a teacher says that if you to a student, if you get 100 on the final, then you'll get an A. So if the student doesn't get 100, he may or may not get an A, right? So the only thing, the only case when this statement fails to be true, it's when the student gets 100. So that is true, but the teacher doesn't give him or her an A. Okay, so basically, if P is true and F is false, then the result is false. Otherwise, it is true. Let's look at an example. Let P be the statement Maria learns discrete mathematics and Q the statement Maria will find a good job. Good job. Okay, express the statement P if P then Q as a statement in English. So if Maria learns discrete mathematics, then Maria will find a good job. That's how we express it. Some common equivalent expressions for conditional sentences. So one way that we learned today is if P then Q. However, P implies Q is equivalent to this. Sufficient for Q, P only if Q, P is sufficient for Q, P only if Q, a sufficient condition for Q is P, Q if P, Q whenever P, Q when P. So really there are plenty ways of expressing the same thing. However, the most common will be if P then Q or P implies Q. Okay. Given P, the sun is made of gas. So the statement for P, the proposition is the sun is made of gas. Q, 3 is a prime number. And as an example, we are supposed to write down P implies Q as a sentence and also discuss the truth value of this conditional. So if the sun is made of gas, then 3 is a prime number. That's what we are supposed to write down in English. So the truth table is, since the proposition 3 is a prime number, is true, right? 3 is a prime number, and the conditional is true. No matter what the conditional, I mean, no matter what the P is, if the conclusion is true, then always this is true because of the table. However, as a remark, the sun is made of gas is the hypothesis, great, and 3 prime is the conclusion. So if you have P implies Q, P is the hypothesis, Q is the conclusion. Also, we note that the logical meaning of this conditional statement is not the same as its intuitive meaning. So in logic, the conditional is defined to be true unless a true hypothesis leads to a false conclusion. So this is how we need to think in order to get it right. So the implication of P implies Q is that since the sun is made of gas, this makes 3 a prime number. However, intuitively we know that this is false because the sun and the number 3 have nothing to do with one another. So when we see P implies Q, the only discussion we need to make is if P is true and Q is false, then the result is false, otherwise it's true. That's all. Okay, the following propositions and their truth values are given below. So this should be all the following. So P is 7 squared is 49, and it is known to be true. A rectangle does not have 4 sides. This is a false statement. Harrison Ford is an American actor. It's true. And a square is not a quadrilateral. This is also false. So this is given to us. And what's the question then? The question is to write down each conditional below as a sentence that indicate its truth value. So evaluate them. First, we are supposed to write P implies Q and then tell whether this is true or false. So if 7 squared is equal to 49, then a rectangle does not have 4 sides. So this is how we write it down. It's not complicated. So the result. Okay, now since we have a conditional statement here, true implies false is false otherwise. So what is this now? So this is true, right? A rectangle does not have 4 sides. This is false. So what's the result then? True implies false is false, right? Here we go. It's false. Okay. The next statement, conditional statement, Q implies R. So if a rectangle does not have 4 sides, then Harrison Ford is an American actor. And this is false, false, true statement. False implies true. So the result is true. P implies R. If 7 squared is 49, then Harrison Ford is an American actor. Both are true, then the result is true. We continue with examples. Q implies S. So if a rectangle does not have 4 sides, then a square is not a quadrilateral. And false, false implies true. R not P. R implies not P. Harrison Ford is an American actor. That's true. Not if Harrison Ford is an American actor, then 7 squared is not equal to 49. Becomes false, and the result is false. If Harrison Ford is an American actor, then 7 squared is not equal to 49, and the result is false. And the last one, not R. If Harrison Ford is not an American actor, so that's false, then 7 squared is equal to 49, and this is also true. Okay, now we have a definition which is about the converse of the conditional statement. So if you are given P implies Q, then Q implies P is called the converse. Okay. We switch Q and P, the places of Q and P. So this is a different thing really. Okay. Contrapositive. Again, we are given P implies Q, not Q implies not P. So this is called contrapositive of this conditional statement P implies Q. So we switch Q, places of Q and P, and we negate them. So we do two things, switching the places and negating. So this is called contrapositive. And the inverse is just negating P and negating Q. So this is called the inverse of P implies Q. Okay. Propositions that have the same true or false values are called equivalent. So if they have the same truth tables, they are equivalent. For example, let's look at this one. This is the implication of from P to Q. And let's take this into account. We have P and Q, not P, false becomes true, true becomes false, false becomes true, true becomes false, not Q, and not Q implies not P. So we are going to use if then here, true, 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 false, true, false. Okay, that's my mistake. This should be true. Okay, let's look at this really. So false implies true. That's the true actually, right? True false implies false. So that's okay. Okay, it's my bad. I'm reading it backwards, so I have to be careful. So you see, not Q implies not P. So we are going from the right to the left. So this is not Q, implies not P. So I'm going to redo my what I said. Okay, just forget about it. So we are going this way. True and true is true. True and false is false. So this is correct. False and true is true. False and false. So we are going this way, really. Okay, fine. So the table is fine. True, false, true, false. Now, if we look at this column, so P implies Q and not Q implies not P. They have the same truth values, right? So if P, Q are false, false, we get true. Here, P, Q are false, false, we get true. And we go like this. There are 4 cases where they are all equal. So what does this mean? It means that P implies Q is equivalent. So this is what we are going to use, 3 lines parallel to each other. Not Q implies not P. So not Q implies not P. If you go backwards, it's here. It's the contrapositive of the statement. So means the statement proposition is always equivalent to its contrapositive. That's what it says. Okay. Sometimes we are going to prove contrapositive. We are going to check the contrapositive instead of checking the proposition itself because it may be easier. We'll see in near future actually. Okay, here are some examples. What are the contrapositive? The converse and the inverse of the conditional statement. The home team wins whenever it's raining. So let us put this sentence, this statement, into this proposition into the form that we are used to. Equivalently, the home team wins whenever it's raining means that if it's raining, then the home team wins. Okay, so this is the P, it's raining, and the home team wins, it's Q. Okay, here we go. Contrapositive, not Q, not P, not Q, not P. So not Q means if the home team doesn't win, then it's not raining. So if we argue logically, we'll see that this is equivalent to if it's raining, then the home team wins. So instead, one may say if the home team does not win, then it's not raining. Converse, switching the Q and P places. So if home team wins, then it's raining. And inverse, meaning not P. So if it's not raining, not Q, then the home team does not win. Okay. We have another one, which I believe it's the last operation that we are going to learn today for propositions. So we can combine 2 propositions P and Q. The combination will be P and if and only if Q. So we have 2 errors. So it goes 2 ways. We have seen this, if then, and backwards again if then. Okay, so what's the truth value of biconditional statement P if and only if Q? Okay, the result of this biconditional statement, if both P and Q have the same value, the same truth value, so if both are true, then the result is true. If both are false, then the result is false, otherwise it is false. Sometimes you call this biconditional statement by implication, so we have 2-way implication. Another way for if and only if, biconditional operation is P is necessary and sufficient for Q. That's another way to express. One more way to express it, if P then Q, and conversely if Q then P. So it goes both ways. P and Q, P implies Q, and Q implies P. So another way of expressing equivalently expressing by conditional operation. Here is the truth table, as we mentioned a few minutes ago. If both are the same, false, the result of by conditional statement is true. If both are true, the result is true. Otherwise, if they are not the same, true, false, or false, true, the result is false. Let's look at an example. Let P be the statement you can take the flight, and Q be the statement you buy a ticket. You can take a flight, you buy a ticket. What is the P if and only if Q? You can take the flight if and only if you buy a ticket. So you put if and only if in between, you connect these two sentences by using this. Okay, and this is true. I mean, if both are true and false, if one is missing, you cannot have the result. Another example, David is son of Ricky, who is male. If David is a son of Ricky, then Ricky is a father of David. So let us show that this is a biconditional statement. The statement can also be written as if Ricky is father of David, then David is son of Ricky. So what does P say? P says that David is son of Ricky. Q says that Ricky is father of David. So P implies Q. So if David is the son of Ricky, then Ricky is father of David. Or P implies Q. Or we may write P biconditional Q if and only if. Okay, here we have something strange going on, so let's fix it. So David is son of Ricky. If David is son of Ricky, then Ricky is father of David. Or if Ricky is father of David, then David is son of Ricky. So here we need to have and also Q implies P. That's what we need, okay? So let me go over this again. Okay, here we have a mistake. So we want to say that P implies Q. Is this really the case? Yes, it is. So if David is son of Ricky, then Ricky is father of David. And we can also say that if Ricky is father of David, then David is son of Ricky. And Q implies P. Both these conditions, I mean these statements, conditional statements, we combine them, which is the case. We can write P upon only if Q. Let's move to the other example. Determine whether the following proposition is true or false. 1 plus 1 is 3 if and only if Mars is a black hole. So 1 plus 1 is the first proposition, equals 3, and Q is the second one, Mars is a black hole. Okay, the truth table of this if and only if statement is when both have the same value. Since 1 plus 1 is equal to 3 is false, and Mars is a black hole is also false, so the result is true. False and false. False if and only if false implies true. Okay, another example. Let P be the proposition a polygon is a triangle, and Q a polygon has exactly 3 sides. And what does the statement P if and only if Q represent? So this says really a polygon is a triangle if and only if it has exactly 3 sides. That's what it means. Okay, and this is going to be the last example. It's interesting, so let's see what it is. The case of the bad defense attorney. Prosecutor says if the defendant is guilty, then he had an accomplice. Defense attorney says that that's not true. So what did defense attorney just claim? So when he said it's not true, what did he claim really? Let's see. First, let P be the claim of, P be the proposition that the defendant is guilty, and Q be the proposition that he had an accomplice. And what does the prosecutor say? He says that P implies Q. And what does the defense attorney says? He says no, it's not P implies Q, right? It just says it's not true. So it's not true that P implies Q. So what does this say? He says no. What's the meaning of not implies P? So let's try to understand this. So P implies Q means P and not Q. Okay, so for the time being, let's assume that this is the equivalent, or it could be a nice homework. We are going to do this in the next lecture, that these two statements are equivalent. Write down the truth tables and check it. Great. So instead of P implies Q, we can write P and not Q, so we negate it. So this is going to be not P or not Q. Again, this will be the second homework to show that these are equivalent, okay? We'll see this in the next lecture also, but for the time being, assume. So not P or Q, what does this mean? This means that, basically in English, the defendant is not guilty, not P, or he had an accomplice. Now, if you see this logical result statement, this brings suspicion. It's still or, it doesn't claim, it's not direct, but it's a suspicion that he had an accomplice. So we have to be careful when we use logical statements or negation of these statements. It may not be might not be good for the person if he's not if she or he is not using the statements negations correctly. So this is it for today. Thank you for following us, and we'll continue with the logic in the next lectures. See you.